We spent the past little while talking about simple harmonic motion. We define simple harmonic motion as motion in which the restoring force was proportional to the displacement. That means that as you stretch something more or compress something more or you pull something back more, the force that wants to pull it back to where it came from gets bigger. The force is proportional to the displacement. Now, what that really boils down to is something that we talked about on Friday, which is called Hooke's Law. Hooke's Law says the force, the restoring force acting on a spring. In other words, when you pull a spring, the spring pulls back, right? The spring pulls back because it wants to go back to its original, its natural position. The restoring force that pulls it back to its natural position on a spring is equal to negative K times X. The bigger the displacement, the bigger the restoring force is going to be. That's really just a mathematical statement of the definition of simple harmonic motion. Hooke's law exemplifies the definition of simple harmonic motion perfectly. Bigger X, bigger restoring force. Now, what's K? On Friday, we said K was a variable known as the spring constant. And the spring constant of a spring or of an elastic or something like a spring or an elastic is a measure of the stiffness of that spring or elastic or whatever. Okay, it's a measure of the stiffness. The higher the value, the stiffer the spring is, the more energy that it can possess or the more potential energy that it can store. The units for the spring constant are newtons per meter. Now, sometimes we're not talking about the restoring force acting on the spring, not the force that the spring pulls back on to get it back to its natural position. Sometimes we're talking about the force that we pull on the spring with, the applied force. Well, the good news is the applied force can be found by virtually the same equation. We would say Fa is equal to K times X. What's the difference? The negative sign. We pull on the spring one way to stretch it. The spring pulls back the opposite way with an equal but opposite force. That's why the equations are the same except for the negative sign. So restoring force pulling it back, negative Kx. The force that we pull it with is positive Kx. Sometimes we don't have the value of K. We got to figure out the value of K in order to plug it into this equation. Or sometimes we use this equation to figure out the value of K to plug it into the next one. The next one that we talk about is the equation for potential energy. The potential energy of this pen right now is due to its height above the Earth. It's gravitational. But the potential energy of an elastic when I stretch it is due to the amount of stretching of the elastic. Okay, we call it spring potential or elastic potential. Sometimes we calculate the value of K using this equation, plug it into here. Sometimes we calculate the value of K using this equation, and we plug it into here. All right? That's it. Okay, that's basically it. We had 5 questions that we were working on Friday, I believe it was, that related to these 2 equations, the idea of Hooke's law and spring potential energy. Those 5 questions were on page 301. Is there any issues with any of those 5 questions on page 301? Okay, 2, 3, and 5 it is. Question number 2 on that page says, an engineer is designing a suspension system for a car. He decides, or she decides, that the coil spring used in this car should compress 4 centimeters when a force of 1,000 newtons is applied to it. What's the spring constant of the spring? And if the spring is compressed 14 centimeters, what force must have been exerted on it? We're going to say F is equal to K times X, or K is equal to F over X. Can you tell me why I'm using Kx as opposed to negative Kx here? It's not really a huge deal. If you used on a test negative Kx here and got a negative value, I probably would mark it right. But we want to be correct with it if we can. We don't want to have a negative when we shouldn't have a negative, if we can distinguish between the two. Why should I not have the negative here? What kind of force are we talking about here? Yeah? It doesn't give me a direction, but more important than that, yeah, we're talking about the force that I apply. When I apply a force, it's positive Kx. When we're talking about the restoring force pulling back, which is equal and opposite, but still restoring force pulling back, we make it negative kx. Talking about the applied force, make it positive kx. Okay, we know the value of F, it's 1,000 newtons. We know the value of X, which is 0.040 meters. And when I do that, that should work out to be, I think, 2,500, isn't it? 2,500 newtons per meter, which we need to round to 2.50 times 10 to the 3 newtons per meter. Now, question B says, if the spring is compressed a distance of 14, what force must have been exerted on it? Once again, we're talking about the applied force with the same spring constant. Don't change the spring constant just because you're changing the force. Okay, that stays as 2,500. We multiply that, though, by 0.14 meters. And we should get, sorry, we got a typo up here. Thank you, Kobe. 25,000 newtons per meter, or 2.50 times 10 to the 4. This becomes 25,000 times 0.14, which now gives me, look at that lightning fast calculation, 3,500 newtons there, which we're going to round to 3 digits, 3.50 times 10 to the 3 newtons. Good. Next question, number 3. So the elastic constant for a spring, or the spring constant as we usually call it, is 750 newtons per meter. How far must you stretch a spring to store 450 joules in it? And if you want to double the potential energy, how much farther would you need to stretch it? We're going to say for this one, EP is equal to 1/2 kx squared. Listen, there's only really 2 equations that we have involving springs, kx and 1/2 kx squared. Looks like we want to use this one since we have potential energy. Rearrange this to solve for x. Becomes EP over 1/2 k equals x squared, or x is equal to the square root of EP over 1/2 k. So that equals 45 divided by 1/2 of 750, and then we square root that. Let's get the number on the bottom first, 0.5 times 750, and then let's say 45 divided by that, and then let's square root that. We get a displacement of 0.3464 meters, and we're going to round that to 3 digits, 0.346 meters. And B, you want to double the potential energy? How much farther we need to stretch it? You tell me what I'm going to do here. Cody? Okay. Yeah, let's make the potential energy equal to 90 and just solve for x again, right? Do the same thing with a different potential. Now that's going to give you an answer in meters, but that's not our final answer. What do we could do to find the final answer, which is how much farther we need to stretch it versus how far do we need to stretch it? Yeah, subtract the 2 of them, right? Get 2 displacements and then subtract them to get how much farther you would need to stretch it. And finally, question number 5 says, when a spring is stretched 0.4 meters from its equilibrium, which is its natural position, if you put a spring on a desk and just left it sitting there, that would be its equilibrium position. So elastic potential energy is 500 joules. What's the magnitude of the force required to produce this stretch? F is equal to kx, but we got to find x. Or sorry, k, I mean. K is equal to, what is k equal to? Comes from, listen, I don't remember what k is equal to, so I'm going to have to derive the equation. K is equal to EP over 1/2 x squared. You get 1/2 in the x squared down by dividing. So let's get the value of k there, whatever it is, in newtons per meter, and then let's plug it into here. Let's get the force. Okay, and then for question B says, if the force is changed to 1,000, how much change in elastic potential energy results? So for question B, let's say x is equal to F over k. K is the same. And it doesn't matter if we're changing the force. The displacement will change as a result of that, but the value of k doesn't. So let's get the value of x And then let's do the same thing as we did in the last question. Subtract them. How much farther would we need to stretch? Whatever we get for this displacement, subtract the original stretching, which is 0.400 meters. Who asked me for question number 5? Good. All right, let's have a look at a different kind of question here. Still related to what we've been doing, but requires us to put a little bit more together here. Question you see on the board right now has a toy car sitting on a hill that's 30 centimeters above the ground, 30 centimeters above the floor. It's not moving. It's attached to the end of a spring, and that spring is compressed. It's compressed 10 centimeters. So picture this. You got this car on top of this hill that's only a foot high. You push it in and compress this spring, and then we're going to let the car go. And what's going to happen to the car? The spring's going to push it forward. It's going to speed up as it leaves the spring. It's going to speed up even more as it goes down the hill. And then it's going to go up the second hill, and it's going to reach the top of the second hill at a certain speed. We want to know how fast it's going to be going when it reaches the top of the second hill. Does anybody have an idea as to what strategy we might try here? By the way, this is where your quiz ends. Okay, this stuff is not on your quiz. What are we going to do to, what are we going to try to tackle this problem with? Yep. Good. That's exactly what we do. Yeah, that's exactly what we do. We're going to say it's a conservation of energy problem where we've converted energy from one type to another. In this case, it's from elastic potential and gravitational potential at the beginning to kinetic energy as it goes down the hill, and then it gets converted partially at least back to gravitational potential energy as it goes back up the hill. So we're going to say EI equals EF. We're going to say at the beginning of this problem that we have two types of energy. Gravitational potential energy because there's a height. And we're going to say that we have elastic potential or spring potential because there's a spring that's compressed, 10 centimeters. It's not moving. After it's released from the spring, it'll be moving. But right now, it's not moving. So that's the total amount of energy that we have. Go ahead. Yes, EI equals EF. Now, on the second side of it, at the end, this is going to be our initial point, right? This is going to be our final. At the end, we have gravitational potential energy again because there is a height, albeit a smaller height. And we have kinetic energy this time because when it gets to the top of that second hill, it's still going to be moving. We do not have spring potential or elastic potential on the second side because there's no spring there. We've got spring potential and gravitational potential being converted to kinetic and then back partially to gravitational potential, but not to spring potential again. Now don't just put in random equations. We know that's a conservation of energy problem. Ollie explained that to us. And we know that we've got certain types of energy at every point. And we know that the initial and final energy will be the same. Let's take a step back from it and look at what kind of energy we have at both points. Ethan? That's a good question. And those questions back in Unit 2 that Ollie was referring to, we could cancel out a mass every single time, right? And the mass appeared in every term, so we could actually cancel it from every term. Here it only appears in 3 terms. Can we cancel it? No. So Rose says, no, we can't cancel it. We can't cancel any of them out. In order to cancel any of them out, it has to be in every term. So we have to stick with the mass here. If we were just sending this car down the hill without a spring, it wouldn't matter how heavy the car was. But since we introduced a spring, it does matter how heavy the car is. The speed of it's going to be affected by that. All right, we get the mass here. It is 0.250 kilograms times 9.81 times the initial height of 0.30 meters plus 1/2 of 30 times 0.10 squared equals, once again, 0.250 times the final height, times 9.81 times the final height, which is 0.18 meters, plus 1/2 of 0.25 times the f squared. That's a little ugly. There's a lot of numbers in there. Do it in steps, okay? Don't try to do that all at once. Let's say 0.25 times 9.81 times 0.3 gives me 0.73575. Okay, that's that number right there. Now let's say 0.5 times 30 times 0.1 squared gives me 0.15. On the other side, we've got 0.250 times 9.81 times 0.18 equals 0.44145. Plus whatever we had over here, 1/2 of 0.25, which is 0.125, times VF squared. Now let's solve this, okay? Let's say 0.73575 plus 0.15. Let's take the 0.44145 over by subtracting. Subtract 0.44145. And now let's take the 0.125 over by dividing. And now let's square root both sides. 1.9 meters per second. So it's at rest at the top of the first hill. That is before it's released. After it's released, it's moving, right? But before it's released, it's at rest. But by the time it comes to the end of the problem, it's moving at 1.9 meters per second due to the hill and due to the spring, both being converted to kinetic energy. If that question isn't that bad, let's give this one a try.
No, thank you.
So here's the deal on this one.
I'm okay, Mr. Dickie. Thanks, Rob.
You're welcome, bud. We'll give it a whirl anyways. So this one has a spring again, and an object, a car, a little toy car on the end of the spring. Spring is compressed, a distance of 0.08 meters or 8 centimeters. It's not moving. It's going to be released. We're going to press a little button. We're going to release the car from the spring, and it's going to be fired away from the spring, down the hill. It's going to speed up, convert potential energy to kinetic. It's going to get to the bottom. It's all going to be kinetic. And it's going to go up this hill, convert kinetic to potential partially, and then back down. And we're going to come down to this spring at the end of the problem, and this spring is going to stop the car at the end of the problem. So at the end of the problem, the car is on the ground and stopped. The question here is, how much does the spring compress? How much does the spring squish? Okay, this is going to be your task over the next couple of minutes to see what you can do with. All right, let's have a look, guys, and see what we can do with it. This question, similar to the last question in the sense that we start off at a height, different height than we start off in the last question, but still a height. Therefore, the initial energy would be due to gravitational potential, MGH. And there's also a spring that's attached to this, which is compressed. Now, having a spring isn't enough to say we have spring potential, but if the spring is compressed, then we have spring potential. So we're going to say MGH plus 1/2 kx squared. We're not going to say there's kinetic energy here because initially, before it's released, there's not kinetic energy. Now, you could have picked a different spot as your initial spot after it's released. Could have been EI, in which case there would have been kinetic energy, but we would have had to do some calculations to find out what V was there. So it makes sense to use when it's pulled back before it's released as our initial spot. And there we don't have any kinetic energy. All right, what about the end here? A lot of people are messing up on this because we haven't done one exactly like this before. When you get to the end, on the ground, we don't have gravity potential because there's no height. We also, in this case, don't have kinetic energy because it's not moving. It reaches the end, the spring compresses, and the object stops. So we have only one type of energy due to the compressed spring, which is going to be spring potential. So it's mgh plus 1 half mv 1 half kx squared equals 1 half kx squared. Cannot cancel out the m's. We cannot cancel out anything, so we got to sub in some numbers here. We get 0.2 kilograms times 9.81 times the initial height of 0.5. 1 half of 25 times 0.08 squared equals 1 half new spring constant of 35 times x squared. So let's do this one here. 0.2 times 9.81 times 0.5. Let's add to that, see some brackets here, 0.5 times 25 times 0.08. Whoops. Why do I want to put the square inside the brackets as opposed to outside the brackets? Matt? Yeah, I want to square the 0.08, not the whole thing there, not the whole equation there. Press equals. Let's divide that by 0.5 times 35. Brackets. And then let's square root that. And we get 0.25. Actually, what do we get? Anybody else get that value, by the way? Yes? Anybody else get this? 0.3. When I gave this to my class this morning, I said 0.25, and then somebody else said, a student said, shouldn't it be 0.3? And he was right. It should be 0.3, not 0.25. How come? It's 0.2? Okay, so it would be 0.2 then, but one digit. That's my point there is it should be one digit. How come it should be one digit? This? Yeah, we get a 0 and a 0, and a lot of people think that's 3 digits, but leading zeros don't count. Okay, so one digit. That wasn't intentional, but then after I gave it this morning, I went, I'll just leave it and see if you guys catch the same thing as that person this morning caught. Okay, since you guys are flying through this stuff, no, I'm having no problems whatsoever. Let's take a look at one more question. There's two parts to it. Okay, listen carefully so that I can describe what's going on here, guys. We got a spring that's compressed, 10 centimeters, spring constant of 20 newtons per meter. Okay, it's compressed, it's squished. The car isn't moving. So why are we finding the speed there? Well, we're not finding the speed there when it's compressed. We press the button, we let this car go. We want to find the speed in two places. We want to find the speed after the car has been released, but it's still at the top of the hill. And we want to find the speed down here after the car has been released and has gone down the hill. So not the initial speed, because the initial speed is 0. We want to find the speed after it's released, and then again, we want to find the speed when it reaches the ground. All right, let's say EI is equal to EF here. We're dealing with the first problem here, right? When the spring is compressed to when the spring is released, how fast is it moving immediately after it's released here? We start off at EI at the initial point when the spring is compressed with spring potential energy, 1/2 kx squared. But we also start off with gravitational potential energy because there's a height, right? 30 centimeters above the ground. Now, at the end of that problem, before it goes down the hill, after it's been released, before it goes down the hill, we want to find its speed. At that point, there's still a height. There's still gravitational potential energy as a result of that height, but now there's also kinetic energy. The spring is no longer part of the equation because the spring has released the car. But we still have a height and we still have kinetic energy. We now have kinetic energy because it's moving. Now, some of you recognize that back in Unit 2 in our dynamics unit when we did energy for the first time, I told you that gravitational potential energy could be defined relative to whatever you wanted. So we could define it relative to here. This is the ground, and it's 30 centimeters above the ground, both before and after. Or we could define it relative to here, which would mean the potential energy here is 0, and the potential energy here, oops, let's try that again. The potential energy here is also 0. It doesn't matter whether you define your energy, your potential energy relative to this spot or this spot, you get the same answer as long as you include it on both sides or don't include it on either side. How many people included MGH? How many people didn't include MGH? Okay, we should get the same answer because potential energy is relative to whatever you want. Let's say 1/2 K, 1/2 of 20 times 0.1 squared is equal to 1/2 of M, which is 0.2 times VF squared. 10 times 0.01, I think is 0.1, equals 0.1 VF squared, and VF is going to equal 1.0 meters per second there. All right, Connor? That's the first part of the question, yeah. We're looking for the speed there in the first part of the question immediately after it's released, before it goes down the hill, right? After it goes down the hill, it's going to speed up, right? It's going to be going faster. We know that we're going to get a V at the bottom of the hill. It's bigger than 1. It's bigger than the speed when we were just released barely at the top of the hill. That's what we're going to do now, is find that speed at the bottom of the hill. Let's say EI equals EF. Now, remember that we can calculate the energy wherever we want, at the beginning or the end or the middle or wherever. It makes sense, I think, to say the potential energy, the energy at the beginning here is 1/2 kx squared, right, before it's released, plus mgh. This time we're going to include the potential energy for sure, because the bottom of the hill doesn't have the same value. At the bottom of the hill, we've got just kinetic energy. So there we go. 1/2 kx squared plus mgh equals 1/2 mv squared. Alternatively, we could have said EI was not before the spring released the car, but EI we could have said is just after the spring released the car. In that case, we would have said EI is mgh plus 1/2 mv squared. And then the final energy would be 1/2 mv squared again. So at the beginning, at the very beginning, potential and potential. At the end, we've got just kinetic energy. K was 20 again, 0.1 squared plus 0.2 times 9.1 times the initial height of 0.3 equals 1/2 of 0.2 times VF squared. Okay, let's get the left side. Say 0.5 times 20 times 0.1 squared plus brackets 0.2 times 9.81 times 0.3. That's the left side. Let's divide that by 0.1, because half times 0.2 is 0.1, and then let's square root that. Then we get 2.6. How many people get that one? You're not a lot? Good, good. All right, so your quiz tomorrow, guys, is not on this stuff. It's on energy, 1/2 kx squared, and F is equal to kx, but not on these conservation problems. That'll be coming up later on, but we'll do another example of this tomorrow to give you a chance to sleep on it, okay? Hopefully tomorrow it'll be a little bit better for those of you who are having a little bit of trouble with it today. Sometimes that's all we need, is just a little bit of a break from it and then come back to it.